Officially, I would like to welcome you all to today's segment of the Meteorological Virtual Seminar Series. And this has, there's actually a project, it's actually a legacy of the GCRF African SWIFT project. And this is a partnership of the Ghana Meteorological Agency and then KNUST leading this seminar series. And we organize this every month, where we bring on board researchers from different fields of meteorology, climate science, and then atmospheric sciences in general to present, findings of their works and how it impacts life, and then it impacts the quality of living and general livelihood. And so today we would again have another presentation by one astute, interdisciplinary climate scientist in the person of that's Dr. William Amponsah. So Dr. William Amponsah, he actually is a lecturer with KNUST, specifically with the WASCAL Climate Change and then the Land Use Center, that's WASCAL CCLU on campus KNUST. And also he's again with the Department of Agricultural and then Biosystems Engineering. And Dr. Amponsah, as we clearly can indicate or can see, he is distinguished in the field of climate science. His research areas are focused more on climate change impacts on hydroclimatic extremes and also climate smart and controlled environmental agriculture for food systems. He specializes in agricultural engineering, hydrology, irrigation, and then water management. And he has vast expertise in different aspects of engineering that applies also into climate and climate issues on a broad scale. And so without wasting much time or taking too much of our time, we would like to give Dr. Amponsah the platform to then begin his presentation today on the topic climatic controls on rainfall extremes and their temporal changes in data-sparse tropical regions. Please, whilst he's doing that, if you have any question along the presentation, you kindly make use of the chat so that we keep this a bit very calm and allow him, we give him the audience to be able to present his work and then his findings also to us. And at the end of his presentation, we then would allow for some oral questions that you can then turn on your mics if you have, you want to really ask the question in a very audible form, then you can do that. Right, but whilst he's presenting, we would want to make use of the chats instead to ask our questions. And then again, if you just joined in, do what to type in your institution so that the organizers will get to know where you are joining us from. And so at this point, we can start. So Dr. Amponsah, you have the floor. I think we'll have 45 minutes for the presentation and then question time would follow. So Dr. Amponsah, are you with us?
All right, thank you very much, Dr. Aye. Good morning to my listeners. Thank you very much, GMET, for inviting me for this very important seminar series. And I'll share my slide. I think Dr. Aye has done incredible work with introducing me. Okay, so today I'll be talking about controls on rainfall extremes and their temperature changes in data-sparse tropical regions. And my presentation will follow this basic outline. So why do we really have to study extremes? And I'll go a bit into rainfall frequency analysis, where I'll discuss some statistical formulations, the generalized extreme value theory or model, and the simplified meta-statistical extreme value model. I'll look at the climate of what we call the data-sparse tropical regions, with focus on Sub-Saharan Africa. With focus on Sub-Saharan Africa. And then I'll talk about model parameters from the work we've done so far, and their extreme quantiles, and then look more into temporal trend analysis of these quantiles and their parameters. I would then look at a steady summary, and I hope we have some decision makers around. So I'll talk a bit about the practical applications of this study and how they can actually help in flood mitigation or flood risk management in the country. Okay, so fundamentally, we cannot talk about extremes without mentioning the concept of climate change. And as we know, climate has been changing, and this has actually been modifying the occurrence frequency and intensity of hydroclimatic extremes. And here we are talking more about drought and floods. So drought are actually on the lower and left side of the distribution, whereas floods are actually on the right side and the upper distribution. And I'm actually a water scientist. I call myself water scientist because I focus on both. When there is a limited rainfall, I'm here to look at how we can develop climate smart or water smart strategies to actually increase agricultural productivity. And when there's abundance, I'm here to look at how we can have some technology, some statistical nomenclature to actually look at how we can mitigate flood impact on the built environment. And Sub-Saharan Africa is very vulnerable to the impact of floods. And there's been an estimated about 27,000 fatalities between 1950 and 2019. And this is because we have very low adaptive capacity when it comes to our river network connectivity, our urban planning, our drainage systems. And then we also have very high sensitivity of our socioeconomic system with tremendous informal sector. So any trigger to the norm, like COVID happened to us, then we have a big problem in the country. We also remember the 2009 torrential rainfall across West Africa that actually affected about 600,000 people in 16 West African countries, from the Sahel, Niger, down to Burkina Faso to Ghana, and we have some hotspot in Cote d'Ivoire. So in Senegal, so undoubtedly, global warming, that is the consequence of climate change, has been intensifying the global hydrological cycle, and we should therefore embrace for what we call the extremes, floods and drought. And today I'll be talking more about the upper tail of the distribution, that is floods. Right? So floods are very difficult to monitor, predict, and model. And this is because on the scientific aspect, the space and time scales of these occurrences are actually very difficult for our typical hydrometeorological networks like rain gauges, stream gauges, and even satellite observations makes it very difficult to model or predict these events. And in the social aspect, you also look at the intricate urbanization, land use change, and climate process and feedback, which we expect to actually exacerbate flood hazards. So the question I'm asking myself and I'm asking you is, how do we really monitor these climate-related extreme floods, and how do we mitigate their impact in data-sparse tropical regions in Ghana? And this is the question, the presentation will actually focus on how we can actually answer this question. All right, so I have this figure here, that's flood regimes in Ghana, and I have a list of floods that actually occurred between 1968 to 2014, which was actually retrieved from a graphic online on the 5th of June 2015. You can check that out. You can also visit flood sites and check out for Ghana or even Africa to look at some of the floods that usually happen. And it's very important in the context of what I've been discussing today, because we are data limited. We have a lot of data problems when it comes to monitoring our hydrometeorological network. So for example, if you look at 2010 alone, there were a lot of flood issues, about 2 nationwide floods. We had 1 in Accra, 2 in Worldview. The same month, we have some in the central Volta region, Afram Plains, and as you can see, these are all mapped on the map on the right side. So I'm looking at this and asking myself, how do we really tackle these issues? One important aspect has to do with what we call the rainfall frequency analysis. Oh, sorry about that. Rainfall frequency analysis. And this is very important in the concept of looking at hydrological systems, right? So when you have a hydrologic system where you have a catchment system, you expect rainfall to come down, you expect runoff to be generated, you expect stream flow to be generated. And here, one of the important stuff we look at is hydrologic data. So if you have hydrologic data, then fundamentally, we are looking at how we can actually look at this data. Sorry, I don't know why my Zoom is. we are looking at how we can actually look at this data. This data is actually characterized by a lot of uncertainty. We have a lot of stochastic processes. It is space and time independent. And within this data, we can look at the extremes in it. So for example, we can have severe storm, we can have flood, we can have drought, which I've already talked about. And we'll be focusing more on flood issues today. So the magnitude of these can actually give a what we call the frequency of occurrence of these through the use of frequency analysis and probability distribution. And this is very important in the design of dams, bridges, and also to determine even economic values of infrastructural activities we do. I mean, I worked as a PhD candidate in a research institute in Italy, and we provided a lot of models and data to actually look at how the design of dams and bridges, and I think Europe uses about around 30 years return levels to actually design years. I think Ghana probably we have a concept there, but we have to start from a basis. So the major objective of this frequency analysis is to actually try to relate the magnitude of extreme events to their frequency of occurrence through what we call the probability distributions, right? So the rationale behind this is that you have to fit this probability distribution to observed extremes, and this will help you to extrapolate intensity, which corresponds to very high, especially about 100-year return levels, or even unobserved quantiles getting to 1,000 years return levels. And the major principle here is what we call the uniformitarian principle, and this is usually applied in genetics, like biological scientists, but it actually works in physical science as well. So we have to understand the knowledge of the past, and with that, if we understand what is happening presently, then we have a chance of predicting future events. So fundamentally, what has happened in the frequency of events in a record are the best indicators of what can happen and its probability of happening in the future. Right? So traditionally, when we talk about extreme value theories, we usually look at the GEV. In the GEV, we can have a type 1, which is the Gamble, type 2, the Frechet, type 3, which is the Worldview. And usually we focus more on the annual maxima series or some peaks exceeding a very high threshold, right? So annual maximum series, all you look at is peak. For example, you can look at the maximum of each year, then you fit models to actually extrapolate quantiles. So even peaks exceeding the threshold for the whole year can have a threshold and look at the peaks that exceed this threshold. But there are problems with this traditional method of approaches. So for example, these are robust theories, and they come up as a result of stochastic uncertainties because the sampling of extremes are characterized by very high uncertainties. That means if you want reliable estimates of high quantiles, then you can only obtain that when you have very high or long records. And if you look at our region, this is one major problem. We have problem with data availability, and even if we have a lot of missing data. And we also have the concept of climate change, and we know the impact on the dynamics of rainfall extremes. So for example, there have been shifts in the dynamics, especially significant changes in both the occurrence frequency and intensity of storms, which makes, for example, the use of AMC, that's the annual maximum series, very misleading in quantifying extremes. And it's basic because there are some years you have long dry spells, there are some years you have tremendous amount of floods. So if you're not careful and you focus on only the maximum for each year, a maximum for one particular year could be not even a maximum in the whole distribution. That can affect the distribution of this series. So there have been the question we ask ourselves: how do we deal with this long record data scarcity problem in our region? And indeed, there have been a lot of studies to improve precipitation frequency analysis by considering large amount of data. So for example, the meta-statistical extreme value theory or approach, which actually has decreased estimation uncertainties compared to the traditional approaches, and also reduced assumptions, have been spearheading. And one important thing is the underlying issues is extremes are actually sampled from the so-called ordinary events. So you can only pick extremes from recorded data. So why don't we just consider all the data points and look at models that can fit the upper tail? Therefore, we increase the amount of data we have in our system. For daily rainfall or precipitation, which I'll be focusing on today, when we talk about ordinary events, we are looking more into wet day amount, right? So any wet day rainfall, which is usually defined to be above 0 millimeters. We consider that as part of the extremes. And how do we fit this? So usually these are modeled using the 2-parameter Weibull distribution, or what we call the GEV type 3, the stretch exponential function. And I'll be focusing on this today. Okay, so when we talk about the Weibull distribution, basically we can look at the tail of it, right, which can be represented by this equation 1, the cumulative distribution function, which has 2 parameters, the scale and the shape parameter. So the scale parameter actually scales the magnitude of the event at all probabilities. And this shape parameter also look at the heaviness of the tail. So when you have higher tail parameter or shape parameter, that means the tail is what? Lighter. And the tail is very important because it controls the magnitude of the stream. So when you have a higher shape parameter, that means you expect lower stream value. When you have a lower shape parameter, you expect higher stream in that regard. And the probability density function is given in equation 2. And here we have 3 parameters describing the stream. 2 of them describing the magnitude, that is shape, and the scale. And then you have one describing the average number of wet days in the system or in a region, that is N here, right? So here we focus on the tail of the intensities. We have all the data records. I'll be talking more about MEV and SMEV, and we understand how this works. But then we are looking at the tail of the Weibull distribution. And here it is better we left censor our daily rainfall data using the case-dependent threshold. So in this case, we'll be looking at how we can distinguish between low values that are potentially wouldn't cause floods, and we can also look at high values which are above what we call this thresholds. All right, so a bit of background theory on what we call the meta-statistical extreme value theory can be found in the Zuzito et al. 2018, and also the simplified version of it in the Mara et al. 2019. And this particular study has been submitted to the Journal of Hydrology. It's actually in the 2nd stage, and I worked with this author here, Francesco Mara, who is a colleague from Italy. I worked with him during my PhDs, and so I'll give a bit of background explanation. I'll try my best to make it very low, not that technical, so that we all grasp the concept. So we've already talked about the annual maxima, where when you have about 30 years record of data, all you do is you have 30 annual maximum because you pick the maximum for each year. So you have a record of 30 years, right? But what the MEV does is it actually estimates the 3 model parameters we talked about, that the shape, the scale, and the number of yearly occurrence for each year, right? And it fits into the Weibull distribution. So you have all the, instead of the annual maximum, you have all the ordinary events, which are defined as the wet day amount. You fit the model, you look at a threshold, which we're talking about, threshold that can actually distinguish between the lower and the upper values of the distribution. And one important aspect is to look at, we look at this each year. So there's a tendency that there will be variation in the parameters, right? So this model is actually non-stationary because we expect changes in the parameters. We expect changes in the trend of the parameters. And the E extreme value distribution for this particular model is computed as a symbol average of this yearly distribution. So you have, if it's 30 years, you fit it for each of the years, and you find the average for each of the years, right? And this explicitly accounts for non-stationary, and this is used in a part of trend detection, which I'll be talking about in a resource session later. And when we talk about the simplified version of it, right? So, and this actually assumes stationarity, and I'll explain a bit further, because fundamentally what we are looking at is we want to have larger amount of data instead of looking at the extremes, right? The extreme or the maximum for each year. So if you have the MEV, which looks at fitting a model for each year and looking at the average of the model itself, we can also have putting everything together. So when you have 30 years and you have every year about 100 rainy days, you can have 30 by 100 data points, right? So you do this, you fit the model, and you define what we call the optimal value. And principally, the MEV, which assumes stationarity, was developed to actually as a limit to MEV. for record length, which is tending to 0, especially as we are trying to solve problem with data scarcity and missing record in our region. And this is with the aim of being non-stationary, but in this particular study, we applied it in a stationary fashion. And this is because we computed the parameters for all the years together. So we don't expect variability to actually happen. And I have to admit that there's a lot of information loss here due to the stationarity assumption, but this is actually counterbalanced by the gain in the estimation accuracy. Okay, so I put this here and just to understand how these three works, the AMC, the MEV, and the SMEV. So I use the stations in Accra, Kumasi, and Tamale, looking at the coastal belt, the middle belt, and the northern belt. And as you can see, the observed annual maxima, which is actually picked from each of the years, actually plotted using the Worldview distribution. Whereas, of course, the stationary model, the SMEV, the non-stationary model, the MEV are also plotted using the same Worldview distribution. And as you can see, for example, Tamale and Kumasi, you can see that the SMEV is actually an ensemble of the observed annual maxima. The advantage is now we are enlarging the data. We are bringing all the extremes, whether they occur within years or between years. Whereas the annual maxima just looks at just the annual for each of the years. Usually the MEV has been found to actually, the non-stationary model has been found to actually overestimate because we look at each year independently, which makes it a bit non-stationary in this regard, right? So, like I said, this study is an article which has been submitted to the Journal of Hydrology. It's on a second review, which we expect it to be published as soon as possible. So the aim of the study was to characterize the controls on extremes in data-sparse tropical regions using what we call the simplified meta-statistical extreme value formulation. And specifically, we apply this to look at how we can validate the robustness, because this model is actually robust, and the underlying assumptions in tropical climate. It has been applied in a lot of different climate, arid, temperate, and looking at our disadvantage in terms of data scarcity and missing record. I think we have to look at how we can have the entire ordinary events, because like I said, extremes are sampled from this ordinary event. So why don't you fit a model to it and try to look at whether the model represents the symbol of our annual maxima. And also to look at the relative advantage it might present with respect to traditional approaches in terms of uncertainties. We also want to quantify and qualify the climatic and attitudinal controls on these extreme rainfall statistics and quantiles, and evaluate and investigate past trends in the extreme statistical or statistics and quantiles, right? So the study is actually very important because I focus on Ghana for the start, but this can be extended to other tropical regions, because if you look at the Kubingega climate classification here on the insert here, right, you can see that fundamentally Africa is divided into about 3 major climatic regions: the arid, which constitute about 57.2%, looking at the northern part of East and Southern Africa. And when you talk about the tropical regions, we look at about 31%, predominantly in our region here, that is West Africa, Central Africa, and part of the East Africa. We also have some temperate regions, part in the Eastern Africa and Southern Africa. So our region here, that's Ghana, is actually, as you can see from here, it's the blue shades, right? So we have what we call the AW code, which is tropical savanna. And then this is the light blue aspect, and we have AM code, which is the dark blue tropical zone. So fundamentally, if we put this study in the concept or in the context of tropical regions for some West Africa, because our climate is determined by latitudinal belts, but definitely this can be extended to other countries in the same region. So I had conversation. I've been working with GMET, especially Mr. Samuel and we've had extensive discussion on this, especially how the data, the quality of this data can actually be well controlled, or can be, better use of word, be validated. And I think they use this tremendous climate data app, which actually looks at how the quality of these are controlled, look at extremes or outliers in data. But from about 73 stations, rain gauge data that we had, we also put it under scrutiny to look at how we can control the data. And fundamental criteria we use here was based on the record length and the missing data. So for example, if we have, for each year, if we have less than 10% of missing data, so about 365 days, we expect to at least miss about a month of data. In some situations, I'll talk about the trend in terms of when you have the peaks, where we are looking at the extremes. So for example, in Kumasi, if we miss the whole of June, then there's a tendency that there'll be some bias, and we can actually eliminate this particular year from it. So the valid years are actually years with less than about 10% of missing data. And stations with record length of such are considered to be valid, right? And then we consider stations with record length of at least 30 years because we are looking at the climatic context of it. So we need at least 30 years of data. So you know we had about 66 rain gauge stations which are distributed in the figure regions, which are actually adopted, typically adopted in Ghana, and these are controlled by the attitudinal belt. So around slightly above 8 degrees north, we have the Savanna zone. Around between 8 and 7 degrees north, we also have the transition zone, and we have the forest zone covering the western coasts of Ghana and the middle belt, and we have the coastal zone, right? So it's very important because these are characterized by certain elevations. So as you can see, we have the Volta basin region, which actually majority part of it lesser than about 200 meter above sea level. We have the coastal basin level around this area, the dotted line here, which is also below 200 meters above sea level. And we have this western patch, which is between the Volta catchment and the coastal basins. And usually the stations here are on elevation. So this is not drawn according to catchment boundaries, but according to the elevation of the various stations in the region, right? So in Savanna, we have about 12 stations to work with, transitions about 10 stations, forest about 37 stations, about 7 stations to work with. And our data record of 1960 to 2019, 2020. And we made sure that for the trend analysis to have a common period of between 1978 and 2018, right? So we look at about 34 years of data within this period. And, you know, we had about 48 rain gauge stations from the total valid years of the 66 stations. And I'm saying for valid years because we had 66 out of the total of 73 stations we had. Okay, so this is just about, you know, the trend, the seasonal rainfall trends in the different climatic regions we have in Ghana. So as you can see, Savanna actually usually peaks from July to somewhere September, right? So when doing this, we considered all these, look at the months. If you miss some of these important months, then there's a tendency that you might be missing some of these, and we were very careful with it. But usually we missed some of the low intensity like November, December, January, February. And in all the data contained, record was less than 1% total or 2% missing records, right? So as you can see, the Savanna zone has a unimodal rainfall pattern, whereas the transition forest and coastal zones have a bimodal rainfall patterns, right? Okay, so I talked about the Worldview distribution, and this is a typical example for Accra. How do we actually look at what we call the optimal value? How do we distinguish between the ordinary events that actually live censored in the lower elevation and also in high elevation? So as you can see from the figure on the right, you have daily rainfall and you have its probability of occurring, right? So we have the left censored data, which are the black dots, and we have the sampled annual maxima, which are actually the red dot. The Worldview distribution is the dotted line. So it gets to a point here, which we describe as the optimal value here, right? So here, the optimal value, and what this principally means is that we are looking at a situation where our sampled or our observed annual maxima less than 5% of it, right? So there's a probability less than 5% of this actually fall within our distribution or our sampled annual maximum. And with this is the optimal value distribution we had. And to be specific, we had about 66 plus or minus 11%, right? For Savanna, we had about 57 plus or minus 24% for transition, 60 plus or minus 22% for forest, and 70 plus or minus for the coastal region. So in effect, the optimal value, so if we had a regional optimal value here, looking at all the data records here. So for here, we have about 7 out of 12 of the station having a quantile over 60%. So what it means is 40% of the ordinary events actually represent the upper tail of the distribution. So in effect, if you have about 30 years and you are using 40% times 300, 40% of 30 times 365, then you have more data to actually look at the dynamics, which will include majority of the extreme value, whether it occurred in year or within years. We had the same for transition and the same about 65% the original optimal value for the forest and 80% percentile original value for the coastal zone. So as you can see, in effect, we had about 15 from the forest to about 40% of the ordinary event, that is a wet day amount, which actually contributed to the upper tail of the distribution. And fundamentally, we left, if you look at the left sensor data in the map here, right? So these are the actual values, and the regional values are trying to regionalize the optimal value. So how do we define the upper tail of this distribution? And the left sensor values here between the at the site threshold, that is the values in figure 9, and the regional values here produce practically indistinguishable results, which means the parameters estimated from the model, there were not that much difference, or the difference was that quite insignificant. And therefore, we use this threshold, the original threshold, in estimating the model parameters in the subsequent presentation, right? So here I looked at the relationship between the coefficient of variation, which represent the uncertainties in the SMEV, and the GEV. You know, the GEV, we look here more about looking at the annual maximum series, right? And fundamentally, as you can see, we have the Savanna, which are represented by the red dots. We can have the circle, which are the 20-year rainfall quantile, the triangle, that's the 50-year rainfall quantile, the squares, which are the 100-year rainfall quantiles, right? And so fundamentally, you would have for A, we use 5 years of record. So for example, if you have 30 years, then we do about 1,000 iterations, look at how 5 years can actually estimate or extrapolate these rainfall quantiles, right? For B, we use 10 years. For C, we used 20 years. And the idea here is to look at how, when you have limited or data scarce condition, how can we actually extrapolate high quantiles? So for the 5 years, you can see that even the SMEV has uncertainties or coefficient of variation up to about 25%, and it actually decreases as you use more rainfall records. So for the 10 years, you have about 15%, and with the 20 years, you have about 10%. But if you look at the GEV, we are moving about 80% for 5 years, about 60% for 10 years, and about 20%, about 45% for the use of 20 years. So undoubtedly, the MEV distribution outperformed the GEV in terms of uncertainties. But like I rightly said, if you have limited data to extrapolate high quantiles, then you have a problem. But if you have more data records taking care of all the climatic variability, then this represents a very good aspect or model for us to adapt here in the data sparse regions. I also presented this the figure here to look at standard deviations, looking about 100 bootstrap iterations of the SMEV and the MEV. And as you can see, if you, the MEV basically, like I've explained, looks at how you can fit the model per year, and you look at the ensemble of average of the years, right, to represent the MEV. But SMEV puts everything together, fits the model for that, distinguish between the low intensity events, the high intensity event, looking at using the optimal value, fits the upper tail of the distribution, and extrapolates what we call the quantiles from this. So basically, for the SMEV, you can see that there wasn't much difference when you have very low quantiles, right? So the two, I mean, the MEV has higher uncertainties compared to the SMEV, but then it's actually exacerbates when it gets to very high quantile. We're looking at up to about 80 standard deviation compared to about 25 standard deviation here, right? So we use these regional values to estimate the parameters. And I've already talked about the scale parameter, the shape parameters, and the scale parameters actually looks at the intensity or the magnitude of the event. So in probability perspective, the magnitude of the event actually increases as we move from the north savanna to the transition to the forest, to the coastal, and we follow the same pattern with the shape parameter. And as the shape parameter, like I said, increases, that means the upper tail or the tail of the distribution reduces, and therefore the quantiles will decrease. So we expect higher quantiles in the forest coastal zones compared to the savanna zone because it increases in that direction. And what they amount, we have very high values for forest. That means the rainy days in the forest actually about 115 with a standard deviation of 19 days in the forest. The transition has about 96 plus or minus 9, coastal 80 plus or minus 16, and the savanna about 79 plus or minus 10. So you can see the number of wet days actually has higher in the forest zone, moving to transition and coastal before savanna, which I think depicts the climatic conditions in the country. For the rainfall quantiles, basically, because of the shape parameter, we have an increase as we move from 22 years to 10 years to 100, because we expect higher quantiles for 100 years compared to 2 years. And for the quantiles, although number of rainy days in the forest, the maximum, you can realize here that we have very high rainfall quantiles, about 89 plus or minus 6 millimeters. That means, what it means is for every 2 years, there's a tendency or probability of this amount of rainfall occurring in the coastal zone, right? And we come to the forest about 89 plus or minus 16, the transition 81 plus or minus 10 millimeters, the savanna 78 plus or minus 5. Let me make a bit of a clarification here. Fundamentally, when we say quantiles, 2-year quantiles, it doesn't necessarily mean every 2 years this particular rainfall will happen. It means there's a tendency that this would happen in every other 2 years. So if it happens now, then at least we should expect that for the next 2 years, at least we have one of them happening. Therefore, we should look at the other 2 years from the next day to the next 2 years. The 10-year quantile actually increases in that order, and the 100-year quantile also increases in this particular order. Okay, so look at the climatic dependence on these parameters, the scale, the shape, the yearly occurrence, and the rainfall quantile. And here, because it actually increased systematically, I'm representing only the 2-year rainfall quantile. And I'm only showing a significant trend. As you can see, we have very low coefficient of determination. That fundamentally means a lot of factors actually goes into explaining this variability, right? And one thing I have to note here that, for example, if you look at the quantiles, you have about these 3 values here, which are very high quantile, but very low latitude. That means close to the coast. And these are actually the 3 stations along the western coast, the Axim, Half-Axim, I think one of the stations I forgot, but on the western coast, which are characterized as part of the forest zone. But they are on the coastal zone. These are actually characterized as very, very high streams. So I think the meteorological scientists, detailed meteorological can actually explain this. But if you look at other stuff with high uncertainties, this is actually within the transition zone, but very high quantile compared to the normal trend. And these are actually stations along the Volta River Basin. So the ones on the coast and the one along the Volta River Basin actually have very high quantile. And this can be explained by the moisture fluxes from these water bodies, right? But importantly, we had significant trends of p-values for all these regressions less than 0.05, which means at least the slope of these trends are not zero, they're not equal to zero. And therefore, the explanation, the minimum explanation, for example, if you look at the quantile, about 17.8% are actually significant. We have other factors that would also explain this variability. We talk about the elevation. We also have other factors like meteorological conditions, like I just explained, the river water fluxes and moisture fluxes along the coast and in the water basin. So the scale parameter actually.
We have 10 minutes, please, if it's okay.
Okay, that's fine. That's fine. So if you look at the scale parameters, right, they actually increase about 0.05 millimeters per degree of latitude. The wet days actually also decreasing. So as we move from north to south, from north to south, you have the number of wet days actually increasing, right? So as we move from south to north, that's we are increasing the latitude. So about 7 days per year per degree of latitude. And the quantiles about 4 for the 2 years, 7 for the 10 years, and 12 for the 100 years, respectively. For this, the relationship with altitude, that is elevation, to be precise, there were no significant, that means the slope of the trend was 0 for the scale, the number of wet days. That means altitude do not really influence the magnitude of it or the number of yearly occurrence, but it has impact on the shape parameter, which is very important in the estimation of the extreme quantiles. And as you can see, the values here, we have about 0.046 millimeter, small magnitude for each meter of elevation for the 2 and other quantiles respectively. So we also look at the trend analysis. So like I said, because the SMEV assumes non-stationarity, we use the MEV, which actually extrapolate for each of the years and look at the assemble average for the year. So we did the at-site trend analysis using the classical Mancano test and looking at the non-parametric sense slope estimator for the rate of change, right? We also did the regional analysis to look at whether within a particular region we can have systematic change in the same direction of the parameters and quantiles. So the figure here actually looks at whether for the stations we have changes, and look at the scale parameters. We have about 87, more than 87% with no significant changes. We have the shape parameters about 91% for no significant changes. The end event over 70% no significant changes. So very high value for no significant changes. And if you look at especially the observed annual maxima, there were no significant changes at all in terms of decreasing, but there were about 2 point increasing changes. So we can be certain for the fact that at least there's no significant changes in significant decrease in observed annual maxima for Ghana. And I talked about this demarcation, the dashed lines, looking at the Volta Basin area, the coastal area, and the hilly area. And fundamentally, we have 3 homogeneous regions which we have demarcated according to the altitudes, right? So for the regional trend analysis, we have this for the whole of Ghana. We know that rainfall quantiles for the 2 years to the 100 year, the annual maxima series are actually homogeneous in the region, though they are not significant. The scale parameters, the parameters of the Worldview distribution and the average number of occurrence are not homogeneous in the whole of Ghana, and they are not also significant. The coastal zone looks similar to that of Ghana, but at least they are homogeneous in terms of the intensity or the magnitude of the event happening. For the hill zones, which are between the Volta Basin and the coastal zones, we have homogeneous and significant model parameters. We have decreasing trends of the quantiles. They are homogeneous in the region, though they are not significant. And most importantly, when it comes to the Volta basin, you have significant and homogeneous increase in quantiles. And this is because we have homogeneous decrease and significant decrease in the Weibull parameter estimation, right? So basically we have increasing trends in the coastal basins and the Volta basin, though they are only significant in the Volta basin. So to conclude on this study, if I move to the practical applications of this, we can actually say that the ordinary event, which are considered as the wet days, that's the raining days, all the raining days for each year, and therefore for the whole data record, are used to actually model the stream rainfall quantiles in the tropical regions. And the Weibull distribution will approximate the tail of this distribution with very reduced uncertainties. The statistical parameters and the rainfall quantiles actually significantly depend on latitude, that has been proven, because the climatic zones are actually demarcated on the latitudinal lines. We also have homogeneous patterns in regional trend that actually depends on the altitude or the elevation of the area. And one important finding of this study is that we realize that extreme daily rainfall amount in the Volta basin and the coastal basin are increasing, but significantly, these are increasing for the period between 1978 and 2018 for the Volta basin. So I'll rush through some of the practical applications of this, right? So fundamentally, we know that the observed increasing trend in the stream rainfall amount in the Volta basin should, and that is the next step we are looking at, should be tested using spatially distributed global or regional reanalysis for providing a lot of product in the system, right? And usually we try to look at the root mean square with observed data. But if we have set trends, then we can look at which one of them can actually reproduce this trend, because there's a significant increase, in the daily rainfall amount between this period. Another aspect has to do with the fact that we know that there have been increasing occurrence of floods in the coastal and water basins. And this actually look at how this increasing extreme quantiles from this study can actually confirm to this trend. We also look at using climate models to actually investigate and quantify changes in future precipitation, because if past records have been increasing, we can actually also project into what we expect in the future. And one important aspect is this study has been a basis for this NASA Serbia proposal, which we actually in the second stage, on how to use machine learning approaches in flash flood forecasting in West Africa with satellite observations. And a team from the United States, from Florida Institute of Technology, Oklahoma University, and George Mason University are teaming up with WASCAL University, which I'm involved with. I think Mrs. Markey from the Ghana Meteorological Agency, who is I think the deputy director, and Sylvester Owusu or Darkon from Hydrological Services Department. And this is a basis because we've realized that there has been an increasing trend and significantly in the Volta basin. And therefore, there's a need to look at how we can actually look at flash flood forecasting in West Africa using Ghana as a case study. So this is for the policymakers who are listening. And I think, for example, Ghana, we need a flood agency to facilitate the activities, make it a more integrated approach for Ghana Met to focus more on meteorology and therefore rainfall coming down. Hydrological Service Department focus more on runoff generation. So if we have this agency, then we can look at how to facilitate activities, such as how to develop quantitative precipitation forecast, how to use models to transform rainfall into runoff, looking at flood response, look at the probabilistic treatment of hydrological data to develop what we call the regional growth curves, and how to use these growth curves to actually make scientific decision support systems. And the scientific decision process should focus more on vulnerability assessment. That's how to demarcate flood-prone areas, looking at river network connectivity, mark out infrastructure vulnerability, look at divergence, how we can create artificial lakes or dams for water supply, irrigation, and or hydropower production. And finally, how we can look at the trade-off or synergy between surface and underground drainage systems in some of the most vulnerable zones in the country. All right, thank you very much for your attention. And MC, Dr. Ayi, I'll hand over to you. I'll be looking forward to answering any question the audience might want clarification on. Thank you.
All right, thanks a lot, Dr. Amponsah. That was a very excellent one. I believe we all followed, and we definitely have some questions to ask Dr. Amponsah while he's here so that he can respond. So we would then make room for question time. And if anybody has a question, you can kindly show by hand. We call you, and then you then can ask your question. Alternatively, you can also ask it in the chat, and then we can then address them. So anybody to start it rolling, please. All right, so Dr. Amponsah, let me quickly ask. So with regards to the extreme detection, and then, so let's say in the analytical aspect, we are able to identify these events. Now, with regards to impact, is there any sort of impact assessment of these historical events that you were able to characterize? And then once you're able to map or sort of match that with impact assessment, then we can see that, okay, then in the near future, if these events are probably going to be more frequent, then we should have this magnitude of impact again, or I mean, how it's going to affect us, I mean, generally, because we the policy makers, or we the ones more in stakeholder ends, we are thinking of how this has an impact or a direct impact. I mean, be it direct or indirect, this has an impact to us. So is there anything that from your study you can then hammer on for us? Thank you.
All right, thank you very much, Jeffrey, for your question. So if you look at flood frequency analysis, in a broader perspective, rainfall is very important because usually in our region, floods are caused when there's a lot of rainfall, right? And we look at this frequency analysis to look at vulnerable areas where we have potentially very high rainfall. But when it comes to flood itself, we also have a lot of intricate processes. So for example, land use change, we can look at our urban planning and those kind of stuff. But the first important thing is to look at the rainfall coming, which regions actually are expected to receive more rainfall. And how do we integrate this in our planning? So for example, like I said, we have to look at how we can transform rainfall into flood response, looking at the urban absorption, the land use changes, and all these intricate processes. And if we can do that, then we can match responses, flood response, that is the discharge which is expected for every millimeter of rainfall in a particular area. And this will be very important in what we call the flood design floods, right? So if you want to build any bridge, then we have to refer to it. Like I rightly said, in Europe, they have about 130 years return level of discharge, right? In all infrastructure activities they do. I might, you are a policymaker, I presume you might also have a value, but it's about time we look at how climate change is actually impacting this. So for example, I did a study when I was doing my PhD in Italy, in Geneva. About 50 years ago, they used about 50-year design flood to do a bridge. And there was one flood which produced 2 times that particular discharge, right? So we have to look at it in a broader perspective. And the important thing is to identify these vulnerable areas. And this study actually confirmed to the fact that we know that there were a lot of tremendous flood events in the coastal areas, most of them also in the Volta basins. And this study using the SMEV, right, which looks at the broader perspective of all ordinary events, has detected that there's actually increasing trend of rainfall amount in terms of quantiles in these particular areas. But more significantly, it is more significant in the Volta basin. I hope I've been able to answer your question.
Yes, exactly. All right. So, Doc, I think there's another question also in the chat. So from Bubakar, and he's asking, so you model the runoff or flood by Bayesian approach. Is that the case? I believe that's the question, yeah.
Okay, so fundamentally, this study, like I said, is a basis for this flood frequency analysis, right? And I modeled not the runoff, but the rainfall quantiles by the Bayesian approach. Because the next step is actually to look at how we can transform this rainfall, identifying where we have hotspots into runoff. And this requires a lot of hydrological models, which we'll be using the EF5, I don't know whether E5F, I don't know whether you've heard about it. But this study looked at how to actually capitalize on the real rainfall data we have in terms of looking at the rain gauge we have, because even if we want to move into satellite, which are characterized by a lot of uncertainties, we will still require these data to actually validate these. So it's about time we understand the raw data we have. Though we have limited coverage, we have a lot of missing data, we have a lot of short records. This approach, the SMEV approach, presents a very good, should I say, a very good analytical framework for us to even focus on the limited data we have. So WASCAL is not really about runoff, but it's about understanding the precipitation synopsis in the country, which the next approach is actually to look at how we can model it using rainfall hydrological models. Thank you.
Okay, yeah, I think there's an additional one. So I don't know if the question is captured right. So is climate type or region impact modeling? So I believe the person is trying to find out if it's more of a climate modeling or climate impact modeling so far that you've conducted. I don't know if the question is clear enough.
Yeah. I mean, from 1978 to 2018, we can all agree to the fact that the climate has been changing. Well, we date climate change back to 1950 onwards, right? So looking at the past events between this, if definitely there has been an increase, which is quite significant in the Volta basin, then we can attribute some of this to climate change, right? So I'm not really sure about the question, but is he trying to say climate projection, or I believe climate actually impacted the trend which was detected in this rainfall quantiles.
Okay, so Bubak, I think if it's possible, you can reframe your second question. That would really help. Okay. And then there's also another one. So you said the rainy days are decreasing by latitude. So is it same for the intensity? Yeah.
Okay, so let me use so for the rainy days, like I said, they are decreasing. So let me maybe latitude. So the rainy day, this what we have, the N is actually decreasing by latitude. That means as you move up north, the total or the average amount of rainfall or the yearly occurrence is actually decreasing, right? The same with intensity, because as I've represented here with the 2-year rainfall quantile, the intensity or the quantiles, I'll put it in that way, the quantiles are actually also decreasing in that respect.
Okay, so that means it's quite variable for.
Yes. Mm-hmm.
Oh, okay.
Yeah.
All right. So I believe your question is answered, MA. There's also another one from Mitio that says, with a flood influence on agricultural practices, so which of the statistical analysis will be more suitable for irrigation and then drainage projections?
Okay. I think I just saw this question before I answer that. Permit me to go back to MAA's question. So you said the rain days are decreasing by latitude, and you want to find out whether it's the same
for the intensity.
No, the rainy days are quite different, right? Mm-hmm. The rainy days are quite different. You can have lower rainy days, that is just counting the number of days we have greater than 0.1 millimeter. Well, these are different. From this analytical framework, like I said, the scale parameter actually scales the magnitude of it, right? So here, as you can see from figure 12A, you have the scale parameter actually increasing with latitude. That means the intensity, though we expect the intensity in the upper part, in the upper latitude, are smaller than what we have in the lower latitude. The intensity in the upper part actually increasing, because the scale parameter is increasing. But the shape parameter, which actually estimate or influence the quantiles, are also increasing. And as the shape parameter increases, it decreases the magnitude of the quantile. Oh, how does that has answered the question? So someone also want to find out whether with the flood influence on agricultural practices, which of the statistical analysis will be more suitable for irrigation?
For the drainage projections, yeah.
Statistical analysis for for irrigation and drainage projection. So we are talking about two different things. Irrigation, that means we are looking at the other tail of distribution. And I think with drought we can still use the SMEV, but we'll be looking at more of in a seasonal sense, not a daily sense, because you can't really predict drought indices on a daily basis. So it should be seasonal basis, either 3 months or 6 months or 12 months, looking at how the intensity of drought varies. So I think that still the SMEV can be used, because the fundamental problem here is that we have very limited data record and a lot of missing data. So why don't we just look at the whole entirety of the data we have and look at how we can fit a model, probability distribution model to it, and therefore in order to extrapolate quantiles, right?
Okay, and then Doc, just a quick one, maybe a follow-up question on the very first one. I mean, the one on the rainy days, and then also that of the intensity. So you see, you were using the SMEV as a more sort of a stationarity approach, I believe.
Yes.
Yes. So
the SMEV.
Yeah, the SMEV. Yes.
Yes,
Exactly.
Yes,
so
yes.
So is that the main reason why it can be used for the intensity? Because I mean, if you're talking of intensity, then clearly you're looking at rainfall intensity not being too stationary then, because I mean your covariances are not going to be quite similar all throughout the periods. Exactly. Yes, but then for the events which are, for instance, the rainy days, and then also the various characterizations of the events, is that the reason why the SMEV cannot fully represent that of the intensity per se? Yeah.
Yes. So John, I made mention of the difference between the MEV and the SMEV, right? So the MEV is actually a non-stationary model, because it is applied on a yearly basis. And we look at the assembly out, expect variations with time, because the models and the parameters for year one would definitely be different from the parameters for the other years, right? The SMEV was introduced to actually look at the default in this MEV due to limited data. So when the amount of data is moving to zero, right? And it was done in the fashion of non-stationarity. But we applied it here in the fashion of stationarity, because we lump everything up. And if you lump everything up, that means we are missing some information, especially the yearly variability. But then it is catered for by the limited uncertainties we have in the approach in that, right? So the MEV will be best to detect how intense the whole thing is. That's why we have the trend analysis here. And like I said, majority in terms of the intensity, that's the annual maxima, we have about 0% that there's no decreasing significance in the annual maxima values, right? But we also have about 97, almost 98%, no significant increase or decrease in the annual maxima value. So it becomes a bit complicated when we are talking about intensity. But for intensity, with the SMEV, we look at the scale value, and rightly, it is actually increasing with latitude. That is, as we move from south to north, the intensity of these particular streams are actually increasing.
Okay.
I hope that is clear.
Sure.
But then the quantiles itself decreases with latitude. So more or less, we have very low rainfall in the north compared to the south. But over the years, the south has been increasing, the north has been increasing. It doesn't mean it has reached the level of the south, but it has been increasing more than the south has been. I hope that is clear.
All right, sure. That's clear. There's another one in the chat. It says, so how does the topography affect these parameters. So
okay, so I'll go through this quickly with this particular. So what we did with the trend analysis was to look at one, how within each station or at each station, how things are changing, whether there's significant increase or significant decrease, right? And we realized that there's no particular pattern. So for example, if you look at observed annual maxima, like I said, there's 0% decreasing significant, about just 2.5%, few of the data points are increasing. So we came back with the idea of looking at the visuals. So if you look at this particular graph here, the visual interpretation of it, you can see that in this particular area, let me use a model maxima. If you look at this particular area, especially along the Volta demarcated with this dashed line, you can see a bit of increasing significance, right? So you can have some triangles in there. You can have here some decreasing significance. You can have here also some increasing significance with a z-score, right? So when you have more red, that means they're increasing. When you have more blues, that means they are decreasing. And we try to look at, okay, putting all these stations together to make it more like a regional approach. How does these stations actually work? And if I can go back to, I could go actually impacted, right? And of course, we found out that in the Volta basin, there's significant increase in the rainfall quantiles between 1978 and 2018. In the coastal areas, there is increasing trend, which is not significant, right? And in the hilly areas, we have decreasing trend, which are also not significant. So the impact of topography on this wouldn't be on a regional basis, but I would characterize that as the location of the rain gauges.
oh, okay, all right. So I believe some of your question is answered.
Yeah, I'm okay. I'm okay.
All right, okay. So we have another one from Bubakar again. So the question is, so if I have to reproduce this study, that's the exact same study, maybe over a different region, which data and then tools should the person then use? Or be your recommendation?
I mean, so the SMEV is a known approach, but I have the code in MATLAB. I also have, I don't know, for the data, it depends on where you want to reproduce it. So it should be area specific, right? If you want to reproduce this in Ghana, then you have to look for data from GMET, which I think is not public data. So you have to go to GMET for that. And for the code, for the tools, I have the source codes here. So if there's anything, we can team up for any region at all you want to do this. So if you're in a different country, that means you have to use the data in that particular country. But then for the model, the SMEV model is I have the code, right? So we can work together if there's any form of collaborative agreement.
All right, sure. I think there's a hand up. Okay, so Emily, feel free to ask your question.
Yeah, so it's just a follow back to the intensity and then the rainy days discussion that was already ongoing. There was also a study by Amponsah et al. On then they tried to analyze the meteorological analysis of flood in Ghana. So these studies basically look at two areas, for example, Accra and then Kumasi. So I'll use this as a reference point of discussion to what has been discussed here as well. In that paper, it was shown that like the raining days, which from your studies are now rather showing they are decreasing per latitude. In that one, it's almost it's rather the reverse from that study. But in terms of the extremes, if you look the coastal area, which is Accra being one of the areas chosen, shows like in terms of the extreme has the first three highest compared to this Kumasi area, which is within the forest zone. But I'm seeing that to be kind of like opposite to what has been shown here from your results. So taking Kumasi, you've even shown us some analysis for Accra, Kumasi, and then Tamale. So looking at Accra and then Kumasi, what will you say in that regards to this study?
Okay, thank you very much.
Did you also notice the same trend in terms of, let's say, taking Kumasi and Nkrumah, for example? Have you checked the stream values, like from historical? Has Kumasi recorded the highest stream compared to the coastal sector or the northern sector per your study?
So let me use this stream analysis, for example. So here, I've actually read. I work with Samuel, so I've read that article. But I think Samuel actually focused on one particular flood event which happened, I think 2000. And Samuel, will you come up with 2018?
Yeah, exactly. Right? It was 2018. Yeah. Yes.
For 2018, and I think Samuel's analysis was. Let me use better use of like a bit robust, looking at a particular flood event, looking at the dynamics, the synopsis of the rainfall characteristics, and came up with a threshold, right? Which is a bit problematic. I'm not saying it's wrong, but it's a bit problematic because if we are to use this particular threshold for any decision making, we know that we are developing, we are expanding. Floods do not happen because we have a particular rainfall amount happening. It has an intricate relationship with land use, land cover here. And these are actually on the regional basis, right? They're on a regional basis. So you have forest zone where you have Kumasi, you have more rainy days, but you have a standard deviation. The coastal zones has lower rainy days, with also standard deviation. When it comes to this particular, which is the latitude, so as you move from south to north, you move from latitude 4 degrees to about 11, depending on the position of the stations. So here, clearly, we are looking at, in terms of this trend line, a decrease, which p-value, which is very significant. That means the trend is not zero. And therefore, we can say this 22.6% of explained variance actually can be attributed to what? Latitude, in terms of explaining the yearly number of occurrence, right? But there are a lot of uncertainties. For example, if you look at Kumasi, Accra will be part of the coastal areas. Kumasi will be part of the forest areas, right? So you can have a situation where a coastal area would have very high yearly number of occurrence compared to a forest area. I'm here to look at the two, whether Accra has higher or lower. But if you look at what I use with the annual maxima series in this particular issue, you can realize that for each of the quantiles, and these are quantiles, right? These are quantiles, these are extrapolated. So we have a lot of uncertainty, but you can see that even the annual maxima series. So for example, if you look at the 10-year quantile, you have about less than 200 here, right, for Accra. If you look at the 10-year quantile, you have almost 100 millimeters here for Kumasi, which means in terms of quantile, Accra is actually has higher quantile, which has been proven that coastal areas are expected to experience more rainfall amounts compared to the hilly areas such as Kumasi. MA.
Yeah.
Maureen. Okay, so.
Yeah, so but I also recommend that, which actually in that paper they were not really looking at the flood, trying to look at the return periods and those, but they were just looking from the concepts of the meteorological conditions. And I think in the conclusion it's also mentioned that most of these floods are more due to human activities. If we should look at the rainfalls actually, and if we should put our systems in place, well, it will have reduced those flood impact. So I think it will even help for policymakers to take the right decision, how to even distribute resources to be able to manage disasters and other things related to extreme flood. I think it would be good if you can break this down to maybe stations or cities which are more prone to this flood event. And when we look at it, maybe lumping them into the regional concept.
Regional.
Yes, that might.
Yeah. So if you understood, if you follow the presentation, right? So here, this is where we have the individual stations, right? And if you want to look at the trend, which we use the MEV to look at the individual stations, it gives almost negligible results. As in, where do we expect for each particular station? Where do we expect trends to actually increase, right? But then if you look at it on the regional basis, like I've demarcated, so you can look at, we have consistently the same direction. And this is very important because you can't really focus on Accra as there's a rain gauge in Accra, and you're focused on Accra because the Densu River, is it Densu, which characterize the Accra catchment, actually starts somewhere from Suhum or even above Suhum, going to Koforidua, right? So it's more of a regional concept, and the river network connectivity, because you expect as a catchment or a drainage area, whatever amount of rainfall coming from the up hills will move directly to the low hills. So it's not really about the spot of the rain gauge, but it's about the region we find ourselves in. And this is always characterized by topography, because we expect a catchment to be characterized by topography, so that we have higher elevations, catching water and moving them to lower elevation. So I think regions are very important. And if we identify these regions, which we have in this, then we can look at how we can demarcate the individual catchments within the regions and pay more attention to that. So if you focus only on Accra, you're using a station in Accra. It could even happen that flood didn't occur in where you have the station, because it's a larger area, right? So you look at on a regional basis, and that will give better information on what to expect in the future and what to do with this particular information. Thank you.
Yeah, thank you very much.
So,
can I make the last one? That I think looking at the conclusion is looking like we are having now two kind of concepts. Like looking at it from the hydrological point, it will be good to look at a wider area, looking at the catchment area. We're also looking at it also from the methodological point of view too. It will also be very good to a little bit break it down so that those, because it's going to be there, we need to consider more stations. But in trying to understand the variabilities which vary from location to location, it will be good. Then the conclusion should be breaking down into both meteorological point of view and then the hydrological point of view, so that it will aid policy making and then decision making very well. Yeah, thank you.
Okay, thank you very much. So I think I'll respond to this briefly. So, you know, this is a study, and I provided a study summary based on the results we found from the study. But I also provided what I call it practical applications, or in other words, the future perspective of this particular study. And the first one is actually to use global or regional analysis products, right? So more, we should move from the point data to look at rainfall product that can actually detect the trends which has been detected in this. That's one thing. The second one is, we can also say that, I mean, development has been increasing in the coastal areas, development has been increasing in Volta basins, and we also can attest to the fact that there has been increasing occurrence of floods in these areas, which actually confirms why we have increasing extreme rainfall values. In the future, we can also look at how to use climate models to actually look at changes in the future. And more importantly, like you are talking about, this study looks at the meteorological aspect, just how the rainfall actually fares, right? We've submitted a proposal for this NASA CVR program, and we are now in the second stage. And we'll be using machine learning approaches for flood forecasting. And this is exactly what we'll be doing. So now we have detected some of these changes. We want to use satellite observations to convert rainfall into flood response so that we can make forecasts. So it's not just enough to focus on rainfall, but to try to convert it to flood forecast. And in doing that, you have to consider land use aspects, right? So like Sammy rightly said, it is not just the rainfall, it's about development issues. So you can have the same amount of rainfall in two different locations. It might cause flood here, it might not cause flood here, depending on what the land use. So that is another aspect. We are moving more into the hydrological aspect, or should I say the hydrometeorological. Because this study is actually purely on rainfall, which is meteorological. Thank you.
Sure. Thank you, Dr. Amponsah. So I think for want of time, we will just take two more questions. We already have two questions in the chat. And then also on the component of modeling. So Jacob says, I mean, great presentation. I'm interested in using the climate models to look at the projected changes in the extremes, employing the SMEV. So I'm sure, Jacob, maybe you would have to get in touch with William and then have that discussion, I mean, beyond this webinar. And there's another one from John Mark Kwashi that says, is it normal for the rains to start in April as it's being experienced now? I don't know if this directly relates to, if it directly relates to yours, or we have some
Yeah, you know,
yes.
I mean, I think I can, maybe I can give a response and then I'll leave it to the Met guy. So fundamentally, when we talk about the impact of climate change, right, it's really broad and wide, and it's not just, oh, the temperature is increasing, this is increasing. It's about the variability aspect as well, right? So it's actually normal. I don't know. I mean, rainfall style. I showed a graph here looking at the seasonality of rainfall here. So I don't know where you are. Are you in Accra or Kumasi or the north? So April, we actually have an increasing for all the other for all the climatic zones. So April, we have systematic increase, and therefore it's likely we can have rainfall in April or rainfall starting April. But I know in the middle belt and southern coast, ideally March should be the onset of rainfall, but the peak is in June. That's what I know. So I'll leave it up for the native guys to actually take it up.
Sure. So I'm sure someone will be able to add on to this. So in Samuel's final statement at the end, I'm sure someone would address this one, John Mark. So kindly hold on. I think that was a great one to Doc. There's a final one from Meteo again. There's Ernest from Ernest. So Ernest says, so I asked a question relating to irrigation and drainage. That was the earlier question. And so he would want to know the rainfall measurement methods employed in your study for the statistical analysis.
I'm trying to understand the question, but if you say rainfall measurement, so fundamentally, I had a data from GMET, right? So GMET, they have a lot of rain gauges across the country that they take daily rainfall amounts, and I used the SMEV to actually fix the model and try to extrapolate higher return levels from 2, 5, 10, 20, 200 years. This aspect of irrigation and drainage, I think I've addressed it. And when it comes to irrigation, you want to look at when there will be drought so that you can irrigate. And I said, of course, you can use it, but it will be on the other side of the tail, so the lower or the left side of the tail, that's drought, right? And I said you can't really look at drought on a daily basis. We look at flood on a daily basis because we expect higher flood magnitude to occur within 24 hours. You can have river floods that occur 3 days, 1 week. But when it comes to flash floods, to higher flood magnitude, you're looking at 1 day. But for a drought system, we can look at the seasonal. We can have the 3 months, 6 months, 1 year, to look at that defines drought. That'll be for irrigation. But for the drainage, of course, if we expect floods, then we should have systems to actually drain these floods. So it's almost the same. So the irrigation can be looked at as the lower end of the distribution, whereas the drainage can be looked at as the upper end of the distribution in terms of floods. Thank you.
Right. Thank you very much, Dr. William Amponsah. It's been an eye-opener. I mean, sharing your research with us. I believe everybody here has gained something very tremendous, and would like to say a big thank you to you. I would like to hand over to Samuel to do the final, remarks, and then also give us some notices on the way forward for the virtual seminar series. So Samuel, if you're around, kindly take over then. All right, thank you.
Yeah, thank you, Dr. Ayi. We are so grateful to Dr. William Amponsah for the great presentation, and it's actually an eye-opener to most of us here. I just want to address the question that was asked concerning whether it's normal for rainfall to start in April as being experienced now. Like you rightly said, the location is very important. So if it's not clear on the location, that one we cannot say much, but mostly in the forest zone, rainfall normally starts earlier than even April. Yeah, especially if you get to the western part of the country. Yeah, the southwestern part of the country. So it depends on which area you're talking about, you know, in relation to this particular month. So I'll also say that next time we're going to have our virtual meteorological seminar series would be in May. That's the ending of May. And there's also going to be another astute presenter also to give us more information about what research he has come up with. We are going to give you a recording of this particular aspect so that in case you have any further questions, you could also straight away address it to the presenter. But in much as do, I think we need to take a group picture as usual. Normally we have to take it so that we can keep this record straight. So if you could kindly put your camera on so that the the picture can be taken. Yeah, I want to see everybody turning on your camera. Yeah, it's very great having all of you here. So I need a smile. I need a smile. Everyone, please, yeah, turn on your camera. Turn on your camera. Okay. Yes, please, one. I'm taking a group picture, so please take note. Okay, for the next 3 seconds, we'll take another one. Okay, 1, 2, 3. Thank you so much for your time. We are so grateful. Please, if you have any questions, kindly address it to the email that sent you the invitation. So without much ado, I don't know whether we have other colleagues who also want to say one or two, but if not, then maybe we'll just close it. Yeah, Dr. Amponsah, we are so grateful for everything. And we know in the future, when we call upon you again, you will not hesitate to come back and then give us more knowledge on whatever research you have come up with. So without much ado, then
thanks for having me, and I'm grateful.
All right, you're welcome. So Dr. Jeffrey.
Yes, sir.
Yeah, I think we are done for now. So unless you have something.
Oh, no, nothing much. So, I mean, thanks again, Dr. Amponsah, and then to everybody who came. It's been great with you. Without you, we couldn't have, pulled this one off. So thanks, and we hope to see you again when we have the next one of the virtual seminar series. So have a wonderful day and a wonderful week in advance. All right, bye-bye.
All right, bye-bye.
Bye.